The weight of the water is supported by the atmospheric pressure. As you can see in this diagram, the weight of the water is acting vertically down here, and the atmospheric pressure is holding the weight of the water up. And now the next question is, how big a glass could have been used? The amazing answer is, the glass could have been 10.33 meters tall. 10.33 meters. Because that's how much the atmospheric pressure is. Atmospheric pressure is huge. It's more than 100,000 pascals. That's 100,000 newtons acting on 1 meter square. That's how much the atmospheric pressure is. The first idea of atmospheric pressure was given by a scientist called Torricelli, where he used a trough containing water. Actually, he used mercury, a trough containing mercury, into which there was a tube containing mercury immersed, with this end being open. He found that the mercury would drop down but would stay every time to a height of 76 centimeters. So in other words, atmospheric pressure is able to support the weight of 76 centimeters of mercury. And we can calculate the atmospheric pressure knowing that. It's either 10.33 meters of water, and because we know that pressure is H rho G, where H is the height, rho is the density, and G is the acceleration due to gravity, H rho G, the height of water in this case is 10.33, the density of water is 1,000, and G is 9.8, which gives 101,234 pascals. 101,234 pascals. That is the atmospheric pressure. Now in this case, it's able to support 76 centimeters or 0.76 meters of mercury. And you can see that on top of the tube, there is partial vacuum. There is just a few molecules of air that they may have diffused through the mercury. And therefore, the atmospheric pressure is able to support the weight of 0.76 meters of mercury. Another application of atmospheric pressure that's seen in daily life is a suction disc. You see a suction disc which you just put on a surface and force the air out and it stays there. Now, what actually keeps the suction disc there is the atmospheric pressure. Like I've tried to show a suction disc here, and we'll calculate if the force required to lift it up, assuming that the radius is 1 centimeter. So if the radius of this is 1 centimeter, which is 0.01 meter, then from there we can calculate the area, pi r squared. Pi is 3.14, the radius is 0.01 squared. That gives 3.14 times 10 to the negative 4 meters squared. So that's the area. And the atmospheric pressure is acting over that area. And so from that we can calculate the force, because pressure is force by area, which means force is pressure multiplied by area. So that's the atmospheric pressure multiplied by the area. And you see that you get 31.78 newtons. That's the force required to lift this suction disc. That's about the weight of 3 kilograms, more than 3 kilograms. So if we had a bigger radius for the suction disc, it would have been even harder to lift it up. Let us calculate the pressure at the bottom of the deepest part of the Pacific Ocean, the Marianas Trench. And here, the depth is 10,994 meters. And using the formula P is equal to H rho G, that's the height. The density of seawater is about 1,023 times 9.8, which gives this huge number as the pressure in pascals. Now, in order to understand how big this is, let's compare it with the atmospheric pressure. But before we do that, understand that that is just the pressure due to this column of water. Now, on top, there is atmospheric pressure acting, and therefore you have to add the atmospheric pressure to this one to get the total pressure at the bottom of the ocean. In fact, that is called the absolute pressure. The absolute pressure is the total pressure, which includes the atmospheric pressure acting on the surface. All right, so that's the atmospheric pressure acting on the surface, which is 101,234 pascals. And so when you try to find out how many times this pressure is, you got to divide by that number, divide this by that number, and you get 1,089 times the atmospheric pressure. That is how high the pressure is at the bottom of the ocean. Now, just for comparison, the average pressure, I must say, in tires is about 2.38 times the atmospheric pressure. That's all. So, 1,089 times the atmospheric pressure is big enough to crush a human being. That's why we need special clothing, special suits to get there to the bottom of the ocean. Try to think about another consequence. For example, if there is an air bubble at the bottom of a lake, an air bubble, as it rises up, the pressure is decreasing. According to Boyles Law, as the pressure decreases, the volume increases in such a way that the product of the pressure and the volume must be a constant. That is Boyles Law. So we will now try to apply this law and find out how many times the volume increases when the air bubble comes to the surface. Remember that we can apply the same idea for hot air balloons as they rise up in the atmosphere. Because as you go up in the atmosphere, the pressure decreases, and so the volume would increase, which could lead to a dangerous situation where the volume increases so much that there is so much stress on the fabric of the balloon that it bursts. All right, so let's apply this and work out a simple problem. So that's a lake. I'm assuming that the lake is 25 meters deep. And here there is an air bubble. And we want to find out how many times its volume increases when it gets to the surface. So call the points A and B. P1 V1 is equal to P2 V2. That's Boyles Law. So pressure 1 is the pressure here at A, which will be the atmospheric pressure, which is transmitted down from the surface, plus the pressure due to this column of water, which is given by height times density times acceleration due to gravity. So that's why it's 25 times 1,000 times 9.8. So we now get the total pressure at A. This comes out to be this number, 346,234 pascals. And the pressure at B, at the surface, is of course the atmospheric pressure. So that is P2. And so now we can apply P1V1 is equal to P2V2 and find the ratio of the final volume to the initial volume, which is V2 by V1. So that gives, when you divide, that gives 3.42. So that means the volume of the air bubble increases to 3.42 times the initial volume at the bottom of the lake. These are just some of the consequences of atmospheric pressure. I hope you found this interesting, and hopefully this will lead you into more thinking really about the atmospheric pressure and the other consequences, such as when you're trying to use a straw to drink juice, we think we are actually sucking the juice into our mouth, but we're not. All we are doing is removing the air in the straw between the mouth and the juice in the container, because initially there's going to be some air there. When you remove that air, the atmospheric pressure that's acting on the surface of the container pushes the juice into our mouths. So all we're doing is removing that air. And there are other consequences of atmospheric pressure which I hope to bring out in the next